Okay, so this problem right here, we have an equilibrium, and that equilibrium has, of course, a delta G. Um, but remember that typically the delta G for an equilibrium at standard temperature pressure would be a zero if it's actually at equilibrium. However, if you remember where it talked about in your book, and we've actually talked about this before in Gen Chem 2 is when we talked about it. You can make a electrical cell by pushing an equilibrium in one direction. And so, for example, if you have more than the equilibrium concentration of this, it's going to drive the reaction forwards, and that's going to cause your delta G to essentially go down, right? And vice versa, assuming you're considering this to be your substrate or reactant and this to be your product, which is how this is laid out. So what we're doing here is the things that can affect the Gibbs free energy of a system are such wonderful things like the temperature of the system, so we have the temperature there, and the concentrations of your reactant versus product, or your reaction quotient is what it's actually called, if you're curious. And this right here is the book value. And so in all these problems, it's always your book value of some sort of pKa or delta G naught in this case. We're doing delta G naught prime in this case, is going to be modified by a modification factor. And that modification factor always includes some sort of log of, in this case it's a natural log, of your products over reactants. Products over reactants because it's always a reaction quotient, which is similar to your equilibrium expression that you may remember from Gen Chem 2. It's just that it does not have to actually be at equilibrium. And so what you need to do here is you need to apply that formula, which is delta G equals delta G naught, which we're given right there, naught prime in this case, plus R, which is the gas law constant that involves joules. We'll have to get it specifically into kilojoules, so we'll need it in kilojoules per Kelvin mole, because we need to have everything end up in the same units, and all of these are in kilojoules per mole. And that'll be times 298 Kelvin, because that's the temperature for this reaction. That'll then be times the natural log, and inside the natural log is the concentration of your product. You only have one product, and it's only to the first power, so we don't have to worry about any of that. Divided by the concentration of your reactant. Again, it's a 1-1 ratio, so there are coefficients 1 here, and that means we don't have to worry about anything there. We just take product concentration divided by reactant concentration. Okay, so R is typically going to be in joules joules per Kelvin mole. You could have done all of this in joules, but your final answer you want is kilojoules per mole, so it's easier just to convert your R value, which is 8.3145 joules per Kelvin mole, into a kilojoules number. And so what you're going to do here is you have the delta G naught prime right there, plus the 8.314 R value. Right here is the conversion factor going from kilojoules to joules. Remember, your kilojoules is what you want to end up with, so that's on top. Your joules is being divided because you're getting rid of that joules. This then times 298 Kelvin. And then finally times natural log of your product's concentration. And that's your product right there. Again, you just look at this name. That's the one in the product right there. And so that's the concentration you put. Divided by your reactant's concentration. Again, your reactant is right there. That's this one. And there's its concentration. You go ahead and solve. Don't forget to do this stuff inside the natural log first, and then simplify, doing all the multiplications before you do the additions. And then you get a negative 0.158 kilojoules per mole. Remember, a negative delta G means that it is spontaneous, and so you are spontaneously making your reactant. The reaction goes in this direction, to the right. And you are not at equilibrium, if you're curious. If we were at equilibrium, it would have been a delta G of 0. So, just in case you were curious. Let me know if you have any issues or you don't understand anything, and good luck.